Okie dokie, we are going to derive the expression for the potential energy of a two-mass system, gravitational potential energy of a two-mass system, where the two masses are separated by distance r. This is what we're going to end up with the recognition that the potential energy is zero at the position of r is infinite separation. Okay, here's how it works. We need to first of all define a system of two masses. So here they are, m1 and m2. Okay, we're also going to define a coordinate system, and I will do that, and I'm going to call this the r axis, and this position over here where m1 is at r is equal to 0. In a way, I'm going to treat this as a one-dimensional problem. R, as in a polar coordinate system, just stands for your distance from some central point. So in theory, I could have this thing move. So I'm going to have M2 move, and I can have it move to various places on the R axis. If I have it move up and down, I can still measure its distance away from M1. This doesn't have to be one-dimensional, but I'm going to just simplify it and move it out along this R axis. So it's going to be moving in a one-dimensional and along one dimension. Okay. Why am I moving it? Well, because what I'm going to do is use the definition of potential energy, which is that the change in potential energy of a system is equal to the negative of the work done by the conservative force that we're interested in. In this case, that conservative force is gravity. And so what we're going to end up deriving is an expression for the change in potential energy when the system changes state, or in other words, when these things move farther apart or closer together. To simplify matters, I'm not going to move that. Whoops, I just moved the coordinate system. Oh, come on. Okay. I'm not going to move M1 as well. I'm going to leave M1 fixed. So essentially, I'm defining the coordinate system as having the origin of the coordinate system at the location of M1. So M2 is going to be the only one that's moving. And so here we go. So I'm going to just move this definition over here for right now, because I'm going to be using this space. So here's the process. The change in state is that M2 is going to move from one place to another place, like that. And I'm going to move it farther away. So I'm going to move it from a close position to a farther position. And there's a reason for that, which I will get into to some extent. I'm a little bit tight on time for this video, so I might just say that there's a reason for that. So let me define some stuff here. Here's the initial position of M2. And I'm going to call that position R1. And then M2 is going to move out to a new position, which I'm going to call, with great imagination, R2. So the process then is M2 moving from R1 to R2. And we will find the change in potential energy of this two-particle system for that process. Okie doke. So let's go. Definition of the change in potential energy, delta U, is the negative work done by the conservative force. The conservative force is gravity, and so the gravitational force exerted between M1 and M2 has a magnitude Fg of big G M1 M2 over R squared. Remember, that's the magnitude. And of course, this force changes as M2 moves out from position R1 to R2. So to find the work done by that force, I have to use the integral form, the work formula, integral of F ds. Now, here's the thing. This is also, normally this would be a dot product, but since I'm in a one-dimensional coordinate system, I can take care of direction simply by there being positive or negative. And here's an important point, is that the ds here stands for the infinitesimally small steps that this mass moves, because this thing is experiencing a decreasing force as it moves out to R2. To find the total work done, I have to move it a little tiny step at a time of ds. And ds, if I were not constrained to one-dimensional motion, recognize that ds could be sideways, or it could be at a diagonal. So I'm being careful not to. I'm not putting dr there because, as I say, the ds vector, if I move it straight from R1 to R2, one of the little ds steps is along the r-axis, but it could possibly be, again, if I'm moving it off of the axis, the ds could be in that direction. So ds is the tiny little vector step that this thing moves from one position to the next. dr, I want to point out, has a very specific definition. Dr is a little tiny piece of the r-axis. So dr has to point, this is a dr vector, has to point away from the origin. And because it's a little tiny step along the r-axis. So, okay, so let's, by the way, the ds is going to turn into dr in a second because we're being very careful to move from r1 out to r2. All right, so let's plug stuff in here. Delta u is negative integral. I'm going to do this as a definite integral because I'm moving from r1 to r2. The force is, and again, I'm not going to do this as a dot product. I'm going to deal with the directions of these things by their sign, positive or negative, along the r-axis. The force, of course, is pointing back towards the origin. This is the force on the force on N2. And so that is going to be a negative g m1 m2 over r squared. And then I'm going to write ds because this thing is moving along these little steps, where ds is a little tiny vector, little tiny step in some prescribed direction. It turns out for this particular problem, though, that because I'm moving straight along the r-axis from r1 to r2, ds is dr. They're the same thing. They both point in the same direction. They're both infinitesimally small. So for this, because of the way I'm doing this problem, I can say that ds is equal to dr. If I were moving from from r2 into r1, my ds vectors would point in this direction, and then for this problem I would write that ds is equal to negative dr. So this is, as I said, we have to be very, very careful with directions. And as I said in class once, I think you just want to make sure you make an even number of sign errors. Okay, I have to finish this fast. Okay, so at this point, then, I think we're ready to do the integral, which is fairly straightforward. r1 to r2 of negative g m1 m2 over r squared. And this is now dr for arguments stated above. Okay, I've got two minuses. They go bye-bye. Let's pull out the constants, g m1, m2. We're integrating dr over r squared from r1 to r2. This is g m1, m2. The integral of dr over r squared, that is, of course, the integral of r to the negative 2 dr. And so that is, the integral of that is negative 1 over r. And I'm evaluating that at r1 and r2. Because I'm doing this as a definite integral. I'm going to bust up the u, delta u as being u2 minus u1, because that's what it is. And I now have g m1 m2 times negative 1 over r2 minus negative 1 over r1. Okay, plugging in the r2 and the r1. Okay. It'd be very tempting, by the way, over here to say, oh, I've got minus a negative 1 over r1. Why don't I make that positive? Well, I'm not going to do that for the following reason. And the following reason is that I am going to, I'm going to now at this point, and we're done in a sense, but what I'm now going to do is I'm going to define that the potential energy, that I have written up here at the top. This is a definition. I'm making this up. I'm going to define the potential energy of the two-particle system as 0 at r equals infinity. And I'm going to now make the position r2 not just some distance away, but I'm going to make r2 at an infinite distance away. And so now I can sub in to this last expression that I wrote. So I have u2 minus u1, but u2 is equal to 0. So I have 0 minus u1 is equal to g m1 m2 times, okay, I've got negative 1 over r2, but if r2 is approaching or is infinity, negative 1 over R2 becomes 0, and I have minus negative 1 over R1. And so now my zeros are toast, and I have negative U1 equals all this junk times negative 1 over R1. So one of those minus signs goes bye-bye. And now I have, where'd it go? U1 is equal to G M1 M2 times negative 1 over R1, or the familiar result that we have, U1 is negative G M1 M2 over R1. And so that is my function, U as a function of R, because R1 can be any value of R, so I can just write this in the general form. U as a function of R is equal to negative G M1 M2 over R, and I am happy.